We talked about how to calculate the magnetic force that acts on a current carrying wire lying within a magnetic field. But of course, if you allow any charge to move, you have a current. Those charges don't have to be confined to move along a wire. As long as I have any charge and it's moving, I have a current. So we can think about the magnetic force acting on a charge that's moving in a magnetic field. So instead of having a current carrying wire, we have a single charge that's moving in the magnetic field. I can calculate the magnetic force acting on that charge with this equation. So again, the magnitude of the magnetic force acting on the charge that's moving in the field is going to be equal to the absolute value of the charge times the speed at which it's moving times the strength of the magnetic field times the sine of an angle phi, and in this case that angle is defined to be the angle between the velocity vector of the charge and the magnetic field vector B. Just like we saw before, this equation still tells us that currents feel magnetic forces. It's just currents are moving charges. So we're not writing it as there's no explicit I sitting here, but that current is being represented by Q times V. So we have moving, that's the V, charge, there's the Q. So moving charges feel magnetic forces because, of course, moving charges, aka currents, cause magnetic fields. So this simply confirms what we said before, which is that the magnetic force is an interaction between currents. It's just in this case we're choosing to let one of those currents simply be a single moving charge. That's the magnitude of the magnetic force that acts on my moving charge. What if I want to think about the direction of that force? Well, again, part of what this sine term is hinting at here is the fact that there's something different going on that's telling me that the magnetic force is perpendicular to the magnetic field. So just like with our current carrying wire, I have two vectors that are going to define a plane. In this case, they happen to be the velocity vector of my charged particle and B, the magnetic field. And so I will have a right-hand rule just like before. In this case, I'm going to put my thumb in the direction of the velocity vector. I'm going to put my fingers in the direction of the field still, and my palm will push in a particular direction. Now, the one additional detail that I'm going to need to deal with in this case that I didn't have to deal with when I thought about the current carrying wire is I need to ask myself, what is this charge? Is it positive or negative? And if it's a positive charge, then the direction my palm is pushing and the direction of the magnetic force acting on the charge are the same. If my moving charge is negative, then the magnetic force will be in the opposite direction as the direction my palm is pointing. So it's one additional little detail that I'm going to need to keep track of in terms of figuring out the direction of the magnetic force that acts on my moving charge. The more important detail to make sure we all understand, of course, is that the magnetic force is still perpendicular to the magnetic field. When we think about that magnitude equation, again, that sine phi term matters. And so what it's telling us is that the relative directions of the velocity and field vector matter when you think about the magnitude of the magnetic force. So when the velocity vector points in the same direction as the magnetic field, or the velocity vector of my charge points in the opposite direction of the magnetic field, then phi is either 0, same direction, or 180 because they point in the opposite directions. The sine of either of those values, 0 or 180, is 0. And so this is a situation where no magnetic force will act on the charge. So if you have a charge that's moving along the field line, it will not feel a magnetic force. On the other hand, if your charge is moving perpendicular to the field line, so the magnetic field still points to the right, but now I've switched it up so that the charge is coming out towards me in the way I'm trying to draw this three-dimensionally, the velocity and field vectors are perpendicular to each other, which means I'm plugging in 90 degrees for phi. Sine of 90 degrees is 1, and I've made that sine term as large as it can be, so I have the maximum value of the magnetic force acting on my charge. If my charge is traveling in any other direction, So if it's not parallel to the field, it's not perpendicular to the field, but it's traveling in some different angle. So the sine of an angle between 0 and 90 is something less than 1. And so I'll have a magnetic force still. It'll simply be less than its maximum value. Again, to determine the direction of the magnetic force, I'm going to need to use my right-hand rule, just like we did before. And so I'll have my thumb pointing in the direction of the velocity vector, my fingers pointing in the direction of the field, and my palm will point in a particular direction. And I still have to come back and ask myself, for my single moving charge, is the charge positive or negative? If it's positively charged, then my palm points in the same direction as the force does. If it's a negative charge, then the direction my palm is pushed points in the opposite direction as the direction of the magnetic force acting on my charge. So we're still going to have a right-hand rule that we're going to need to use. We'll just have one additional step at the end that says, is your palm pushing in the direction of the force because Q is positive, or is it pushing opposite the direction of the force because Q is negative?